This summary video is for the AQA Trilogy Science and will cover the content needed for the Chemistry C4 Chemical Change Unit and will only contain material applicable to the foundation tier. The basis of this topic is to look at how substances react together and how these reactions can be practically used in modern life. Let's start with the reactivity of metals. Most metals will readily react with oxygen to form a metal oxide, and we call this oxidation. When we extract the metal from their ore, then we are removing this oxygen, and that is called reduction. On the picture on the slide, you can see that on the left we have copper oxide, which is a compound which is a green colour, and on the right hand side we've extracted from that the pure copper. Metals have differing degrees of reactivity. Here we have a simple reactivity series. As part of the requirement for the examinations, you do need to recall the reactivity series in order. So at this point it might be worthwhile you devising a mnemonic to help you to remember the order. The metals at the bottom are quite unreactive, silver, gold and platinum, so they tend not to react with oxygen, and when we find them, we usually find them as pure metals. The next group up are less reactive than carbon, so can be extracted using carbon. We'll look at how that happens. And then finally, the metals that are above carbon in the series are more reactive than carbon, so therefore they need to be extracted using electrolysis. In this example, we can see the extraction of iron using carbon. So the iron oxide is reacted with carbon in a blast furnace, which is the diagram on the left hand side, and there the carbon will remove the oxygen and we will get iron and carbon dioxide. So at this point the oxygen is being removed, so the iron oxide has been reduced by the carbon, and the carbon will have gained oxygen, so the carbon will have been oxidized. And the reason that this happens is down to the ability to gain electrons. So you'll think right back to when you've been doing atomic structure and bonding, and the fact that elements all want to gain full outer shells of electrons, and that they can do this by transferring electrons between each other. In this case, the carbon is more reactive than the iron, so it will be more able to attract those electrons and form a compound with oxygen than the iron is. So that is why the carbon will effectively remove the oxygen and leaving behind iron. By using this same principle of every electron wanting to have a full outer shell of electrons, then more reactive metals can also displace less reactive metals from their compounds. And so in the example shown on the slide now, we have zinc reacting with copper sulfate. Zinc is a more reactive metal, so it's more likely to gain those electrons. So the zinc forms a compound with the sulfate, and that leaves behind pure copper. If we then go back to our reactivity series, we can see that metals above carbon must be extracted using electrolysis. We also use the process of electrolysis to purify copper. Electrolysis then is the splitting of an ionic compound into its elements using electricity. And you can see here on this diagram that we have electricity, and that the solution is known as an electrolyte, and then we also have electrodes. it's important that if they ask you to draw this setup in an exam, that you actually draw it as a full circuit, including the power supply. So here we have a diagram of an electrolysis practical, which you may have done in the past, and you can see that we have a power source and we have two electrodes called the cathode and the anode, and that the ions are being attracted to each of the electrodes. And if you follow the positive down to the anode, you can see that the negative ions, the anions, are being attracted to that. And on the left hand side, where we have our negative electrode, the cathode, the positive electrons are being attracted to that. The solution, or the liquid, is an electrolyte. Now, students sometimes worry about remembering the names of the anode and cathode, but don't panic. Positive is the anode, negative is cathode. Okay, so positive anode, negative is cathode. Don't panic. Okay, for electrolysis to occur, the ionic compound must be in a liquid form, either molten or dissolved in water, so that the ions can move to the electrodes. Let's now look at a short animation of the electrolysis of molten lead bromide. Let's take a look at the electrolysis of lead bromide. Lead bromide is an ionic compound, so at room temperature it will be a solid. So the first thing we need to do is to heat the solid until it becomes a liquid. For electrolysis to occur, the substance must be a liquid. So here we've heated it until it has become molten and then applied the electricity. When lead bromide becomes a liquid, it will have lead 2+ ions and bromide- ions. These will be attracted to the oppositely charged electrodes. The lead ions, which have a positive charge, would be attracted to the negative electrode, where they would receive 2 electrons and become overall neutral and become a lead atom. The negative bromide ions would be attracted to the positive electrode, where they would give up their extra electrons and become bromine atoms. Bromine is a non-metal and will covalently bond to another bromine atom to become a bromine Br2 molecule. At the end of the process, you can then see that we can separate the two things, because the lead will be a solid at the bottom of the dish, and some of the bromine will have been released as a gas and the rest of it will be a liquid. You can see that the equation for the reaction, lead bromide, will be electrolyzed to form its elements, lead and bromine. So we've used electricity to separate the ionic compound back into its original elements. Okay, so to summarise that, opposites attract. The positive metal ions move to the negative electrode and the negative non-metal ions will move to the positive electrode. Going back to the reactivity series then, metals above carbon in the reactivity series can be extracted using electrolysis, and the one that is most frequently asked is about the extraction of aluminium. You can see that sits just above carbon. So aluminium is extracted from aluminium oxide using electrolysis, and on the right hand side here you can see a diagram of a typical electrolysis cell. So we have the two electrodes. The positive electrodes are suspended in the electrolyte solution, and the negative electrode forms the outer casing. Now, aluminium oxide has an extremely high melting point and it does not dissolve in water. So to get it into a liquid form takes a huge amount of energy. And scientists realised that they could decrease the melting point by adding a substance called cryolite. So aluminium oxide is mixed with cryolite and then heated until it becomes a liquid. At this point then, the products of electrolysis you would expect to be aluminium and oxygen, with aluminium forming at the bottom, being a positive ion, Al3+, being attracted to the negative cathode, the lining of the cell. The oxygen then you would expect to be produced at the positive electrode as the negative 2- oxide ions are attracted to the positive anode. However, the anodes are made of carbon and this is done at extremely high temperatures. So when the oxygen is attracted to the anode, it will also react with it and form carbon dioxide. This doesn't cause too much of a problem because we are using this process to extract aluminium, which we still do. It just means that our byproduct becomes carbon dioxide and not oxygen. And it will also result in the positive anodes being eroded away as that carbon reacts with the oxygen to form carbon dioxide. We also have to think about the environmental implications of producing and releasing carbon dioxide gas. We previously said for electrolysis to occur, the electrolyte needs to be a liquid so that the ions are free to move. We've looked at electrolysis of a solid compound and melting it, and now we need to look at the electrolysis of a solution, because some ionic compounds will readily dissolve in water and form a solution which can then be electrolyzed. First of all though, a reminder that aqueous solutions are ones where ionic substances are dissolved in water. Because we now have another compound present, we need to consider what will happen to that when electricity is applied. And in fact, during electrolysis, water will split into hydroxide ion and the hydrogen ion. This means we've got two extra ions to consider, and only one product can form at each electrode. So now we will have two positive ions in our solution and two negative ions. Let's start by looking at the negative ions then. If the negative ion is a group 7 element, so it's fluoride, chloride, bromide, iodide ion, then this will produce its element at the anode. And this is because these elements are really reactive, and when they react to gain electrons. So they're going to want to gain the electron at the anode. If these elements are not present, then oxygen will be produced using the hydroxide ion from the water. So if we predict the products, if we have the electrolysis of sodium chloride ions in solution, we would have the negative ions would be chloride and hydroxide. And if we compare these two, then chloride is in group 7, so the chlorine will be formed. In this second example then, the negative ions would be nitrate from the silver nitrate and hydroxide from the water. Nitrate is not found in group 7, so oxygen would be produced in this case. If we now return to the reactivity series then, we can see that metals above hydrogen, so we put hydrogen and carbon in the reactivity series even though they are not metals, and metals above hydrogen will not form during electrolysis of aqueous solutions. This is because they are more reactive and therefore will be more likely to lose their electrons to gain that full outer shell. This means that hydrogen will be produced in the form of hydrogen gas instead of the metals. We look at the elements below hydrogen then. In this case, hydrogen is more reactive, so more likely to lose its electron, and in which case the metals below hydrogen in the reactivity series will be formed during electrolysis. So going back to our electrolysis cell, we've said at the anode we produce either an element from group 7 or oxygen, but at the cathode, where the positive ions will be attracted, we need to consider, is the metal more or less reactive than hydrogen? And in this case, the least reactive element will be formed. So looking at examples of this then, if we consider silver nitrate again, this time the positive ions would be silver and hydrogen. Hydrogen is more reactive than the silver, so the least reactive is formed, so we would get silver metal in this case. If we then look at sodium chloride, the ions we would have would be sodium and hydrogen, and in this case sodium is more reactive than hydrogen, so the hydrogen would be formed in the form of hydrogen gas. Metals also react with acid then. Let's have a look at how metals will react with acid.
Here we take a look at the reaction of 6 metals with dilute acid. You can see them displayed here, going from magnesium, the most reactive, down to copper, the least reactive. They are placed in the same order here. I've already added the acid to 5 of them. I'm going to add the acid to the most reactive one, magnesium. Here it goes. And you can see that the hydrogen coming off will ignite. You heard it pop. You may see the flame. Hydrogen is burning. I can see it. You may not see it on the camera here. If I was to give magnesium a score of 9 out of 10, aluminium, which should be the next most reactive, at the moment, due to a thick, stable oxide coating on its surface, it's reacting with a score of perhaps 2 or 3 out of 10 only. In fact, at this stage, the zinc is reacting considerably more vigorously. According to the bubbling I see here, I might get awarded a score of 5 or 6. Here we've got the iron, and all I can see is a slow stream of bubbling coming up from the iron. I might award that a score of 1. With the lead, we just get the very occasional bubble produced, and I would award that a score of much less than 1, perhaps something like about 0.0001, a very low score but not 0. Copper has absolutely no reaction, no bubbles being formed, so I would award that a score of 0. Returning to the aluminium, I'm returning now to the aluminium, and you see the reaction is really taking off. You heard the hydrogen popping. You may see it burning there in the background. So after about 3 minutes, the acid has eaten its way through that protective oxide coating, and now we're seeing the true reactivity of aluminium. And now, instead of a score of just 1 or 2 out of 10, quite happy to award it a score of maybe as much as 7 or 8. So we see here the true reactivity of aluminium with dilute acid.
So we can see that metals will have different reactivities with acid. Because all acids contain hydrogen, then metals above hydrogen will react with acids. And as you get closer to hydrogen, that reactivity decreases. Metals below hydrogen then will not react with acids. When metals and metal compounds react with acids, they produce salts. There are 4 ways of making salts from acids. We can have an acid plus an alkali, gives a salt plus water. An acid plus a metal will give a salt plus hydrogen. An acid plus metal oxide gives a salt plus water. And an acid plus a carbonate gives a salt plus carbon dioxide plus water. So you can see in all of these a salt is produced. In all but a pure metal, then water would also be produced. However, if we've just got a metal, we only get hydrogen. And then a carbonate, because we've got that carbon in there, we can also produce carbon dioxide. We give an example here then. So we've got sulfuric acid reacting with magnesium metal to produce magnesium sulfate, that's the salt, and hydrogen. And here is also shown the symbol equation. The name of the salt is formed from the acid and the metal. So the second part of the salt comes from the acid, and hydrochloric acid will form chlorides, sulfuric acids will form sulfates, and nitric acids will form nitrates. And then the first part of the salt name is whatever metal was in either the pure metal or the metal compound. Looking at some examples of naming salts then, if we look at the first one, calcium hydroxide is reacting with hydrochloric acid, so it's going to be a chloride because it's from hydrochloric acid, and the metal will be calcium. So our salt is calcium chloride. And our next one, magnesium oxide, reacting with nitric acid, it will be a nitrate, and the metal is magnesium, so it will be magnesium nitrate. The third one then, we're reacting it with sulfuric acid, so it will be a sulfate, and our metal is copper, so it's copper sulfate. Next one a little bit trickier then, so it's nitric acid, so it will be a nitrate, and ammonia doesn't contain any metals, but it does form the ammonium ion, so it'll be ammonium nitrate. And then finally sulfuric acid, so it's a sulfate, and the metal is potassium in potassium hydroxide, so our salt would be potassium sulfate. Let's now have a look at this required practical for making soluble salts. So the first step would be to react copper oxide with an acid. So for example, we might use sulfuric acid, and what we do is we add enough copper oxide until it stops reacting, and we know that it stopped reacting because it's in excess and we still have some copper oxide present. We now have all the acid has reacted and we have some unreacted copper oxide, which is a solid. So this means that we have a solid and a liquid, and the easiest way to separate that is using filtration. So we add this solid in excess because it's a very, very simple process to then separate the solid from the liquid. So the unreacted copper remains in the funnel, and our filtrate, the liquid, will then be our copper sulfate salt solution. It is a solution, it's still in water because that was one of the other products of the reaction. So now we need to remove the water. So we place the copper sulfate solution in an evaporating basin above a beaker of boiling water. And at this point we are not aiming to remove all the water from the copper sulfate solution. At this point all we want to do is to concentrate the solution and remove some of the water. Once we've done that, we then take the evaporating basin with the remaining copper sulfate solution that's now more concentrated, and we leave that to evaporate at room temperature. We would then be left with copper sulfate crystals. Acids and bases. Previously, you will have looked at the universal indicator and the pH scale, and the pH scale goes from 1 to 14, with 1 being a strong acid, 7 being neutral, and 14 being a strong alkali. So a neutral in the middle, and as we move from 7 outwards we get stronger. Examples of strong acids then: stomach acid. A weaker acid might be lemon juice, which contains citric acid. Water is neutral. Weak alkalis, things like soap. Slightly stronger alkali, baking powder. And then really strong alkali is oven cleaner. And universal indicator will tell us how strong an acid or an alkali is. So acids are substances that have a pH below 7 and turn universal indicator yellow, orange or red. Hydrochloric acid is a strong acid. Ethanoic acid is a weak acid. But all acids contain H+ ions, and it's important that you remember that. So all acids contain H+ ions. Alkalis then are substances that have a pH above 7, and they will turn universal indicator blue or purple. All alkalis contain OH- ions. So acids contain H+ ions, alkalis contain OH- ions. And sodium hydroxide is a strong alkali, and ammonia is a weak alkali. When we react an acid and an alkali together, we produce a salt plus water. And we've just looked at how we name those salts. So in this case, I have added sodium hydroxide to hydrochloric acid. So I'm going to form a chloride, and the metal is sodium, so it's sodium chloride. Here is the word equation for any neutralization reaction. So an acid plus a base reacts to form a salt plus hydrogen. If we're looking at the ions, acids contain H+ ions, and hydroxide ions are in all alkalis. So when the H+ and the OH- react together, they form water. And this is the ionic equation for neutralization.